All right. Okay. Hello, grade 11s. Sorry about that. I was at school earlier. Yeah, I got back home as soon as I could. A couple of people I have to say hello to. How's everyone doing? I know I saw some of you at school. It was all right seeing you guys, I guess. Hey, Liam. How's it going? Anybody? Well, I figured maybe some people might miss today because they also have a time slot today. Maybe that's fine. Yeah, cool. Uh, I guess let's get started. Same as always, we have our question document. Hey, Liam. Sorry, I said Liam. Mason, how's it going? We have our doc. Pop in your questions here. Even if you have questions about yesterday's stuff, you have it. Yeah, and I know I said I would, but I didn't end up doing it. So let me do that right now. I didn't post the homework at all. So let me show you guys what it will be. So create it as material, color right, hand rule stuff. I'll also post it for Miss Farag in case she hasn't already done so. Maybe I should check. Okay, I'll post it later for Miss Farag if she hasn't done so already. Right hand rule stuff. I'm gonna add Google Drive link. Where's my folder? Here we go. Kyle, hello. How are you guys doing? Electricity lessons. I think it was solenoids and motors. Should be. It's not here. Here? No. Give me a quick second here. Maybe it's in here. No. Maybe it's in the other folder. Give me a quick second here. Unit for electricity lessons. All right. Hopefully this one has it. No. Okay. I guess I'll have to post it after stream. I can't seem to find it right now. One last thing I could check. My recover drive. Here. This one. I think. Yep. Covered. Electricity lessons. Okay, I think this is the one though. Let's go into. Where is it? Here we go. No? I'm lost then. Anyways, I'll post it later. It's basically right hand roll practice. Some stuff we learned from yesterday, and as well as some new things we're gonna pick up today. Today we're gonna introduce two additional right hand rules. They still follow the same principles, but it's a little bit different. We're gonna talk about it. Okay. Let's just quickly check out our question board in case anybody posted something. I'll save that for later. Oops. Right hand rule here. Okay. Explain right hand rule and left hand rule. Sure. Let's actually just get a picture out. Okay, so yesterday we did what was called right hand rule number 1, which is this one here, the cool curl copy image. Yesterday we were talking about something. Okay. Ooh, wow, that's huge. Okay, we talked about what's called the curl right-hand rule, whatever. We said that if we wanted to know, so first things first, if we send a current down a wire, or if we have a current traveling, that current creates a magnetic field. That was Orsted's principle. If we have a current, moving charges create magnetic fields. Where is the moving charges to Kaysen? Hello, good morning. It's afternoon. Anyways, if we point our thumb in the direction of our conventional current using the right hand, our right hand fingers will tell us the magnetic field. But we know that, well, conventional current is not the way electricity actually works. We follow electrons. If we do electron flow, well, the current is going the opposite direction, but the fingers still tell us, well, what the direction of that magnetic field is. So, okay, if we're talking about conventional current, in this case, right to left, if we do this, our thumb is the magnetic field. Sorry, our fingers are the magnetic field, thumb is always the current in the first right-hand rule. In the other right-hand rule, the left-hand rule, if we're talking about electron flow, it will still tell us the same magnetic field because the way we look at it, it comes, let's say, my fingers go up, down, and then under, like that, right? So, left-hand rule for electron flow, right-hand rule for conventional flow. We do conventional in physics unless we say so just stick with right-hand rule. Okay, so this is what we learned yesterday. Oh, yesterday we also talked about into the page and out of the page, just so we can also do 3D stuff. So this, and so circle with dot and circle with X. This one is coming at me, so it's out of page, or board. This one's into page. Okay, cool. Today we're going to extend that further. We're going to talk about right-hand rule number 2. By the way, right-hand rule number 1 will always still give you the right answer, but sometimes it's more convenient to do right-hand rule 2, specifically when we are talking about solenoids. Alright, so maybe we'll just take a quick aside. What is a solenoid? Well, whatever. The wire wrapped around itself in a coil is a solenoid. So a coil conductor, another name for that is a solenoid. A solenoid. Essentially, it's just a wire that's wrapped around and has a hole through the center that allows the electrons to flow. And the reason that manufacturers do this is that because, well, if one wire creates a magnetic field, what if we stack those wires together? And that's how we stack wires, by coiling them. Well, we can amplify that magnetic force. Because not only do we have one length of wire, we have multiple circles of wire that add its magnetic force over its course. Anyways, so right-hand rule 2 says, instead of the thumb being the current and the fingers being the magnetic field, we'll switch it around. So if direction of conventional current, so this is the positive terminal, this is the negative terminal, not electrons. Conventional flow goes from positive to negative. If we put our hand or our fingers along the coil in the direction of the current, then our thumb will point in the direction of the north. So instead, our fingers in this right-hand roll, our fingers are now I, and our thumb, maybe we should do a different color. Okay, let's draw our hand. So our thumb, this is our thumb becomes the magnetic field B, and our fingers are the current I. Okay, yay. Okay. Hopefully people see that. Our fingers become the I. So, as the current is going around the coil, it's producing a magnetic field that's left or right, well, perpendicular to the coil itself. Which way is north? Our thumb points in the direction of north. If we did electron flow, then the hand would be this way, but we would still point to the left here as being north. Everyone okay with that? So conventional current right-hand rule number 2 for solenoids is fingers are current, thumb is direction of north. I'll wait a quick second in case anyone has any questions. I'm going to go to example number 2, and it says label the north and south pole of the diagram. If the gentleman or lady, looks like a gentleman's hands, I guess, if that person is holding the coil this way and in the direction of the current, what should I label the left side? What should I label the right side in terms of north and south? What should we label them? I'll wait in chat for a response. In the meantime, maybe I'll go hunting for those worksheets. I don't know where they are. Like I swear they were there before. Oh wait, yeah, it's here. So it's in lessons, motor right hand rule practice. Ah. Okay, whatever. I found it. I'll give people some time. Okay, maybe we'll make the question really specific. Arrow down is north and arrow. Oh, sorry. Okay. We're using the second right hand rule, Arman. So now we're going to use the arrows here representing the current. So they're telling us that essentially we're talking about a wire that's around a cylinder, and this wire goes behind. Wait, that's drawn correctly. This one's drawn incorrectly. We need another wire here. Okay. The wire goes in front first, then goes behind, then goes back in front, then behind, in front, and then behind. You get the idea until it comes out the back. So if we were to label it first, we would say this is the positive terminal because the the current is coming from the positive side and it goes towards the negative side. That's why the person wrapped the fingers around the way that they did. So behind the pipe, the current is going down. In front of the pipe, the current is coming up. So that's why the person wrapped their hand that way. So right now, we're using the second right-hand rule, which says that the fingers will point in the direction of the current. Since the current is going up in front of the pipe and down behind the pipe, that's how the person oriented his or her hand. The thumb now points in the direction of the magnetic field. So essentially what happens is that we can use current to create a bar magnet. And this bar magnet, on this side, well, the thumb is pointing in the direction this way. Thumb points for north. And then the opposite side will be south. Okay, before we continue, you might be thinking, okay, when will we ever use this? Oh, well, whatever. Specifically, this is solenoids are really important for, well, like I said, magnetic fields in our day-to-day lives, speakers. So if you there we go. If you ever have like a large speaker with you, they normally have a strong magnet at the end. They use a magnet and a coil behind it so that they can move the magnet back and forth, and that's what creates the sound. Maybe we should look for a schematic. Not like that. This is the circuit diagram. We want to look for a diagram. Yeah, the diagram is better. Yeah. Cool. There we go. Copy image. Let's paste that in here. It's not that big, but it'll do. Okay. What they call the voice coil. So there will be a, well, terminals. There's a permanent magnet on the sides. Pens. There's a permanent magnet here. And what they do is that they will send current through the coil. It will go through the coil, and it will produce a magnetic field. Let's say if they produce a north here, if the magnet here is like a north-south kind of thing, that magnetic field will be pushed or pulled by the magnetic field created by the current. And that's what vibrates the diaphragm of the speaker, which makes the speaker kind of go back and forth, creating sound. So we need coils and electricity to do that. A permanent magnet as well helps. Okay. In the next one, we have the north and south. Can you tell me which way is the current flowing? Is it going from right to left or left to right? So reverse the right-hand rule here. Make your thumb point in the direction of north and tell me which direction your fingers go. More importantly, if you had to label this, is it going to do something like this or vice versa? Will it be something like, I'm going to draw the same thing, or something like this? I want to know, is the current going from here, from right to left, or is it going from left to right? In the meantime, let me just post that thing. Let's see here. I was working on it. Okay. Add drive. Start this one. Lessons. Motor principal right hand. There we go. Yeah, this is what I wanted to do. Okay, so this one. Number 1. Number 2. I think that's sufficient. Okay. I'll also post Miss Frag. Left to right says Z. Excuse me. We'll give some people some more time in case they're still working it out. Maybe Arman got the same thing. Cool. Give me a couple seconds. Let me just post these. So yeah. Save, post. Done. Okay. From north to south. So, sorry, from south to north, so from left to right. Yep, okay, let's have a look. Maybe, okay, I'll use my bottle here as my north-south. So we'll say that, I don't know, the spout is the north part. And let's just have a look at how the wire is oriented. The wire comes, is here, is between me and the pipe. So it's closer to me here. And then it then wraps around this way. So, so that's the way that the current is going. But if I hold the pipe that way, I'm pointing towards the south. So no, I need to make it point this way. So the current is going behind, and then when it's in front of me, when it's between me and the pipe, it's going down. So the way we want to look at it is that the current between us and the wire, closest wire, is going down. Because when I put my right-hand rule in front of me, I imagine my thumb is inside the solenoid, inside the coil, and the fingers are wrapping behind the pipe going upwards, in front of the pipe going downwards. So I want to draw it downwards everywhere it's closest to me. So all the visible parts have a downward current. Obviously behind the pipe is going upwards, but this tells us that the current, the conventional current, is popping out of here and coming out of there. So I could then label also this as the positive terminal, this is the negative terminal. So yes, the current is going from south to north, or this in this direction here. Nicely done. Had we drawn the diagram a little bit differently, we could have made the coils, like, let's say, go, if we oriented the coils or the wiring differently, it might be different. But for this wiring and the north to the right, the current, this is the positive terminal, that's the negative terminal. Okay, so solenoids. How do you think we can alter magnetic solenoid? Okay, so how do we create a strong magnetic field or weak magnetic field? So, well, we could either make a solenoid with lots of turns, or we could increase the current. A stronger current will produce a stronger magnetic field. Now, for those, I never actually proved it. Let's actually do it right now. Why does that right-hand rule, this right-hand rule number 2, work? What if I just wanted to do right-hand rule number 1? Yeah, that's possible. Let's say we created just a like kind of loop of wire. I don't know, it kind of looks like a light bulb. And let's say this is the plus, this is the minus. So let's say we did the current this way, right? If we do the current this way, whatever. Okay, you get the point. Okay, so if we put our, so remember, right-hand rule number 1 was that we put our thumb in the direction of the current. So, I wonder if I can sort of do this. Give me a second. I'm going to try something out. Can I make myself sort of transparent? That'd be kind of cool. Let's see, filters. opacity. Okay. I'll like spend another 10 seconds trying to figure this out. If not, then I guess not. Opacity. Image mask blend, maybe? Okay, done. Ooh, hello. What if I do that? Done? No. Okay, never mind. I'd give it a shot. Anyways, so if you follow the wire, if we use right hand rule number 1 and follow the wire, it starts on the right side of the. Is there a pointer or something I can use here? Highlighter? No, it's actually a highlighter. Okay, if we start on the right side where the current is coming in, and we follow the loop around, we see that outside the loop, everywhere we do it, the magnetic field seems to be going into the page. If we follow our thumb, let me draw a hand real quick. So if we followed, yes. If we follow, we use the right hand rule and we follow the current using our finger, using the first right hand rule, we see everywhere outside the loop, we're going to have the current going into the page. So it's going into the page, we want to draw X's, right? And everywhere, if we pull our fingers through the page and back, we see everywhere inside, it's creating a magnetic field coming out of the page. What does this mean? What does that mean? What does that mean? What does that mean? Since all of these are kind of coherent, meaning they're in the same direction, they amplify each other. So since all those magnetic fields are pointing in the same direction, the more magnetic field lines we can point in the same direction, the stronger the field gets. So the more we loop something around, the more we can add to the magnetic field. So that's why increasing the number of turns also gives us a stronger magnetic field. Okay. Last but not least, we're also going to talk about the magnetic force, or the motor principle. So we talked about, well, right hand rule number 1, thumb is current, fingers are magnetic field. So that's normally when you follow a straight wire. And then for convenience, we said we can use right hand rule number 2 when we're talking about solenoids. Then we swap them around. Fingers are the the current, and then the thumb will point in the north direction. Okay, but magnets also have forces, right? So we also are going to introduce right hand rule number 3, which will tell us how to determine the magnetic force. Okay, so like we saw yesterday, well, we can draw field lines for any magnet. If the field lines kind of gel together, like I said here before, if they don't repel each other or bounce off each other, they are going to form an attraction. If we get something like this, where the field lines are fighting with each other, we're going to experience a repulsion. Those field lines are going to push each other apart. So here we get repulsion, on top we get attraction. Okay, right hand rule number 3. I don't shoot, I should have brought a picture. Let's get a photo real quick. Right hand rule magnetic force. Images. You know what? This one is good. Copy image. Control V. Oh, what's going on? Was weird? Can I just paste it? There we go. There we go. So this would be considered right hand rule number 3. It's very similar to right hand rule number 1, but we're not curling our fingers around a wire. Instead, we want to just make our fingers align with the magnetic field that's external. Okay, so let's have a look here. Our thumb points in the direction of the current, like it always has. This is something new. Our palm, 90 degrees to our palm, will be the force. Our fingers, once again, are the magnetic field. So the way we determine the magnetic force on an object is we see what is the external magnetic field doing. So even before we look at this wire here with a cross in it, even before we look at that, we will say, well, let's ignore that for a second. Let's just draw the magnetic field here. Magnetic field comes from the north and goes to the south. But the magnetic field passing through this wire, well, is just directly north to south. Cool. All right, so this is my B. And I ask myself, okay, passing through the conductor, the magnetic field is pointing down. So I would automatically say, okay, my right hand rule, I'll point my fingers downwards. Whoop, oops. Let's go back. Okay, next. My thumb has to point in the direction of the current. That was a cross, I said. It kind of looks like a dot. Let's make it really obvious. I'm going to say that's a cross. I'm going to make that a cross. We can do both. If the current is going into the page like a cross, my thumb will point this direction. And then what happens to the wire? Will the wire be pulled in towards the magnet or pushed away? Well, that's what the palm tells us. If our fingers are pointing down, like the magnetic field says it is, and the thumb is pointing in the direction of the current going into the page, that tells me my palm is pointing towards the left. So the force that this wire will feel will be towards the left. So here the force will be to the left. If we did the same scenario with the current coming out of the page, we would do fingers down for the magnetic field, thumb pointing out of the page, so towards us, then the force would be to the right. Cool, huh? Not cool? I don't know. I think it's cool. Okay, let's just quickly check out our question board. I didn't check it at all today. Let's have a look. Any questions? When is the summative due? Well, I think I put the due date as Friday, but last call for marks might be Sunday. Yeah, Sunday latest. So have everything in by Sunday is all I'll say. Okay. How are we doing? Okay, so no other questions. That's cool. Example number 3. Oh, we just did example number 1. Actually, no. Let's say this is a dot. I want you guys to determine if this is a dot. Where is the force acting on this? I know we just talked about it. But in which direction is the force acting on the conductor? Determine where the conductor will travel. Or rather, determine the direction, the force on the conductor. That's a better way to say it. Determine the force on the conductor. All right. I know we just did it. Whatever. Leave me be. And imagine this, today is our last lesson. Tomorrow we'll go over some of the answers from those worksheets. But today is the last lesson. Crazy, huh? Okay, people are quiet because they're like, probably we just did this. Okay, let's do it again. The magnetic field through the conductor, obviously we said, the field lines do that, north to south. Boom, boom, boom. Okay, I'll get to that in just a second, Arman. And through the conductor, which is the most important, it's going directly from north to south here. Right. What am I thinking here? Why am I brain farting? Okay, right. Fingers point direction just directly down. Thumb towards us this time because that's a dot. My palm tells me that the force is going to be towards the right. Okay. And I'm going to teach you guys the best way to remember that. Okay. Back to this. No. Let me just paste a new one. Right hand rule number 3. There's also another way to do it. Okay. Right hand rule. We call this number 3. So they said right hand rule number 1 here. Let's do a quick fix here. This is right hand rule number 3. Obviously, V refers to the movement of the charge, so that's the same thing as I. This is actually, if you want to calculate the force, the magnetic force, this is the formula. We will not be using that. That's grade 12. But it's something interesting, I guess. Okay, B is still magnetic field. Oh, this is not the... this is not the diagram I wanted. This is the one I wanted. Whatever. Yes, great. We don't need that. Okay, excellent. Okay, so, right. So current is our I. Our field, I don't want to call that field, I'll call that magnetic field. So that's the letter B. And force, F. How do you remember what stands for what? Okay, current and field, magnetic field is the same, like, so, is the same as the right hand rule number 1. Thumb is current, and normally fingers are a magnetic field. Now, the other way of doing the third right hand rule is just to hold your hand like this, because the middle finger takes the place of the palm. Because we always say your palm points in that direction, so whatever, you don't need to use the palm. The middle finger is that, right? So, I, current is thumb. B is your pointing finger for your magnetic field. And then F is your friendly finger. F. Friendly finger is force. So, that's one way to remember it. Your friendly finger is force. Your magnetic field is your pointing finger, and current is your thumb. It's the same thing as, if you just did your hand as well. Just the middle finger takes the place of the palm. So it's actually kind of more visual, I suppose. I don't know. Okay, let's actually use this rule to come up with the answer for this one. If we know the north is here, the south is here, and this wire is out here, we need to analyze in which direction the force will be. I'll come back to that because Arman asked a question. I saw one question in chat. Okay, when doing these questions, how do you determine the direction of your thumb from into the page and out of the page? If you're ever doing into and out of the page, well, you're looking for the circle with X and circle with dot. If this is current, if I said that this is current, I said current and I put B. You know what? Let's do a couple examples. Okay. Make it nice and sweet, short and sweet. Okay. Let's say we have a pipe, literally a piece of wire, and we know that the current is passing this way. If you see the context of this, and they say fill in the dots, what they mean for you to do is, okay, use your thumb to point for current, right hand rule number 1, and the dots will represent your magnetic field. So it will be up to you to determine, okay, the magnetic field, my fingers are doing something like this, where they are coming from the behind, they're going behind and coming from behind in front, something like that. So I would say on top, it's coming out of the page, so something like those are dots. And then when they go in front of us, and now they're going behind, these are going into the page. That's how we determine what's what. These dots and crosses could be in magnetic field. It could mean anything. It's just telling us the direction. We have to determine what they're trying to get at here. If this is current, then we know that we're talking about magnetic field as being this and this as B as well, top and bottom. Okay, so for this one here, same deal. What is the direction of the force? Let's have a look. Actually, we're going to do this in an interesting way. What if we analyze two things? We will first analyze the magnetic field from the magnet itself. So once again, just north to south, north to south, north to south. So just pointing downwards here. So fingers down for magnetic field. This is right hand rule number 3. Now, thumb. I'm seeing a cross. That is going into the page. Into the page is the cross, so my thumb has to point towards my screen or towards my paper. Down, my palm tells me it's going towards the left here. Boom. That's my force. What if, though, we were to analyze it a little bit differently? I wonder, I can't remember if that applies here or not, but let's give it a shot anyway. Let's go home, oops, Control C, Control V. Let's get another copy. What if we just analyze the magnetic fields? Pens. Okay, if we did the magnetic field of the conductor, so let's do the, I changed my mind a lot. Okay, if we did the external magnetic field, that was the one we did earlier. What if we also did the magnetic field of our wire? Very interesting. So, the wire, if you use right hand rule number 1, thumb is current, points towards the page, and it's telling me that the magnetic field around the wire is clockwise. So, if I drew a clockwise current, what would I see here? Wait a second. What do we see here? What do we see? Anything? It turns out here the magnetic field is opposite to what's happening, and here it's in the same direction. That's another way you can go about it. All right. This one over here, I'll give people a chance. Obviously, one of them is north and one of them is south. Let's go for this question mark here. In chat, if we know that the current is going out of the page and the force is given, what is this here? Is it north or south? Okay. North or south? Give it a shot. North or south? Any suggestions? We might have to reverse engineer this. Okay, so let's use the new fancy fangled right hand rule we got. So right now we know only middle finger and we know thumb. We know that the middle finger points in force, so we can put middle finger for force. Then the thumb has to be pointing at me because that current is coming out of the page. So middle finger force, thumb is pointing at me. Okay, I know now my index finger, my pointy finger, is going this way. So I know the magnetic field lines from the magnet on the conductor is going from top right to bottom left. Let me draw that. So if I draw that out, I've actually pretty much solved it already. So I know the magnetic field passing from here to here is that. Well, magnetic fields start from the north and they go towards the south. So hopefully you got something like that. Right hand rule number 3, thumb is current. Pointy finger is your magnetic field. Friendly finger F, middle finger, is force. So force aligned with the green arrow. Then we determined, okay, then the thumb had to point at us. And then now my index finger is pointing along that magnetic field line. So, well, magnetic field lines go from north to south. Therefore, north was on top and south was on the bottom. All right, that's it. Today, I was gonna go. Actually, I will. I'm gonna go through like, well, how does a motor work? Well, a motor works something like this. They have lots of fancy names. Well, we have a power source, so something has to be giving electrons to travel in a loop. As those electrons are traveling in the loop, they're creating their own magnetic field. The fancy word for stator. Stator is a fancy word for just magnet. One end of the magnet. So these are just two magnets, two stators. Stator here, and armature is just a loop. Commutator is, well, just the rotating piece. And you can imagine if we attach an axle to this, now we can, I don't know, drive a wheel or something like that. Okay, anyways, we send a current in. if our, let's analyze just this one over here. Let's analyze the left part of the loop first. The left part of the loop, the current is going this way. The magnetic field line is going this way. So the left part of the loop is going to be pushed upwards. The magnetic force will push it upwards. And then we'll loop around. We'll come back to the part of the right part of the loop, which is coming towards us. And we'll see that, well, the magnetic field lines are still pointing from right to left. Now my palm is facing downwards. So the force is going downwards. So we see that the left side is being pulled up while the right side is being pushed down. We can see how it's starting to rotate. And when it flips sides, well, the same thing. The right side will be pushed down and the left side will be pushed up. And we can see how we can create a motor, a simple motor, using, well, a loop, a wire, a permanent magnet, and a current. Voila. Okay, before I head out, I want to just go through maybe this over here. When we use right-hand rule number 1, and when do we use right-hand rule number 1 and when... Okay, so right-hand rule number 1 we use when we have a length of wire that is straight, not coiled. Right-hand rule number 2 is convenient for us when we deal with solenoids. So, straight wire. Right-hand rule number 2, solenoid. Solenoid / coil of wire. Is 2 for solid. Yep. You had it exactly in the second part of your question. Well done. I wanted to look at the homework I posted. Here we go. So, oh no, I posted the answers. Whatever. I'll post the homework. Don't look at the answers. Try it out for yourself first. I'll come back to that one. This one over here doesn't look good. Why doesn't it look good? Doesn't look good. Let me open it. Is it open already? The answers. Okay, yeah, so this is what your homework will be. You're given all these different directions. You have to determine which letter will exemplify whatever you're looking for. So, determine the direction of the magnetic field. So they want you to figure out what is B, created when we have each of the following wires. So here, the first wire is just, I don't know, going left to right, and the current is going towards the right. Can you figure out which letter will give us this sort of motion? So we will use right-hand rule number 1 here, and figure out using right-hand rule which letter does this. Actually, let's do it in chat real quick. Anyone give me a letter for number 1. If we have a current going towards the right and we get this, which letter does this? Anyone see which letter? Our man says G. Anybody else? Give you some time. Agreed. Okay, so no one else chimed in. Yeah, it's G because, well, when it's coming above, it's coming towards us. H is when it's going below, it's coming towards us. So this one's the above toward us. Yeah, Alexandria, perfect. Nicely done. So that's the idea behind all this whole worksheet. And that's it. So the types of questions we'll ask you on your electricity summative will be dealing with circuits, and they'll be dealing with right-hand rule stuff. In fact, some of them are taken from here. Whatever. Try it out for yourself. You know, be honest. If you want to get the most out of it. If you just want to get the marks, I don't know. Whatever. Do what you want. I'm not your boss. I'm signing out. Okay. Have a wonderful afternoon, everybody. Tomorrow we'll take up the homework.